Hi and welcome. This is Pankaj here, Pankaj Kumar Singh. In the last few videos on probability, we have understood the definitions of probability. We have gone through the different approaches towards probability, and we also looked at few questions. And apart from that, we understood what is mutually exclusive events and independent events. And we also went through conditional probability, isn't it? Those are the things that we understood till now. I have done enough questions, I believe, based on conditional probability. And if you feel that there are more questions that needs to be done, and if you feel there is a question that needs to be explained to you, please go ahead and post it onto the comment section. Just mention the textbook, the question number and the page number, and I'll try picking that up for you. Okay. In this video, I'm going to try and touch upon Bayes' theorem. Okay. Many people are good at Bayes' theorem, and some find it a bit difficult to understand Bayes' theorem. I'm going to try and explain the theorem for you, okay, and probably pick up a few questions based on Bayes' theorem. Before we can understand or try to derive Bayes' theorem, we need to understand total probability. This video is going to be a lot more conceptual, and for us to understand what is total probability, we need to understand partition of a sample space. Okay, so what is it? Let's take a sample space. Could be anything. The sample space could be a sample space for any event. If I can represent that particular sample space as using a Venn diagram, it's going to have this, isn't it? It's going to be the entire sample space, like the universal set. Okay. Now in this, I'm going to make sub events. Okay. Let's say event 1, event 2, event 3, event 4, event 5, event 6. Okay, I'm just making individual events over here. Alright, so I'm calling them as event 1, event 2, event 3, and so on till event n. All these are events, individual events for me. Okay, now if you actually notice these events, none of them are overlapping each other, isn't it? I'm not having an event something like this, which is overlapping this and overlapping this. Okay, I'm not having something like that. Okay, so that is one thing that you need to notice. And not only that, if I take the union of all these individual events, it's going to give me the sample space. Okay, so these kind of events, which gives me the sample space when you union it, union E2, union E3, union so on, union En, which is going to give me the sample space. And the intersection of any two events is always going to be a null set. You pick up any two randomly, you just take the intersection of it. It's never going to overlap each other, and hence it's going to be a null set. These events are mutually exclusive events, isn't it? Because the intersection is a null set, mutually exclusive. Not only that it's a mutually exclusive, it's also exhaustive events. Now why is it an exhaustive? Because the union of it is giving me a sample space. Okay, so basically these are the partitions of a sample space. Okay, so E1, E2, E3 till En are the partition of a sample space. Why? Because the union gives me the sample space, the intersection gives me a null set, and the probability of any event EI is always greater than 0, which means every event has the chance of occurrence. Okay. Alright, now let's move on. With that in my mind, I'm now going to make a statement on total probability. Okay. Alright, let me bring up the NCERT statement on total probability for you. Okay, so that is the statement on total probability. What does it state? Let's understand this. It talks about E1, E2, E3, and En till En being the partition of the sample space. Basically, these are the mutually exclusive and exhaustive events of sample space, and suppose that each of the events has non-zero probability. Basically it states the same condition that all of them have the chance of occurrence, and A be an event associated with S. Then this, okay, let's understand this with help of a Venn diagram. Okay, so this is my sample space, right? This is a diagram I had written earlier. Now I'm going to partition this into events which are not overlapping. They're completely mutually exclusive, and when you take the union of it, it's going to give me the sample space. Now I'm going to consider an event A. Okay, suppose that each of the events has a non-zero probability. Let there be an event A associated with S. So this event A is such that it is something like this. Okay, so it's overlapping all the sample space. I'm going to use a different color for this. I hope that I can actually draw it on that itself. Okay, I think I can do that. Yeah, now this is the event A that I'm talking about. Okay, now this event A is overlapping this, right? Here I'm going to draw a different color for overlapping this. It's overlapping here, overlapping here, overlapping this event over here, here, here. All these are overlapping, isn't it? It's overlapping every other event. So this is my event A. Okay, so this event A, which is overlapping all of them, the event or the probability of that event A is given by this. That's my total probability. Okay, let's look at the proof of this. The proof of it is very, very easy. We'll understand that right away. All right, so I know that E1, E2, in E3, E1, E2, E3, and goes on till En are a partition of the sample space. Okay, so which means that the sample space can be written as E1 union, sorry, not a plus, it's a union, E1 union E2 union E3 union E4, and goes on, union goes on to union En. Correct? Now I also know that I can pick up any two events from this particular set and take an intersection of it. EI, let's say EI, EJ, intersection of it is always going to be a null set where I comma j is equal to 1, 2 till n, any one of these events. That's what this means. Okay, so if that's the case, then can I say an event A, okay, is A intersection the sample space? I can do that, no? I mean, for example, I have a 1, 2, 3, 4, 5 and a 6. So I have defined a subset as 2, 4 and a 6, which can also be written as A intersection the sample space, which will always give me the 2, 4 and 6, the common element. Okay, can I further write this as A intersection of E1 union E2 union E3 union goes on till union En? Correct? I can do that because of this proof what I wrote here. Okay, perfect. So can I further write this as what? A intersection E1 union A intersection E2 union A intersection E3 union goes on till union A intersection En. I can do this, right? Okay, perfect. Now that is my A. I'm not going to take the the probability on both sides. Okay, and here one thing that we need to understand that because E I and EJ, any of the two pairs are completely independent, or I'm sorry, are completely mutually exclusive, even these are events are going to be mutually exclusive. Okay. Okay. Now let's go on. So what is the probability of A? The probability of A is going to be probability of A intersection E1 union A intersection E2 union A intersection E3 union goes on till union A intersection En. Correct? Okay, perfect. Which can be written as probability of A intersection E1 plus probability of A intersection E2 plus probability of A intersection E3 plus goes on. Getting me? So what happens next? Why am I able to write this? Let's understand that first. See, probability of A union B is written to me, it is written as probability of A plus probability of B. Okay, and minus probability of A intersection B. In this case, my A intersection B does not come into picture simply because A and B are mutually exclusive. So this entity strikes out. And exactly why I don't have any intersection on this. Okay, so let's come back here. Alright, so that gives me probability of A intersection En. Okay, perfect. But I also know that multiplication theorem on probability, what does it state? It simply states that probability of A intersection E1 can be written as any event, actually not only A intersection E1. If you can generalize and write this as B, okay, if I can generalize and write this as B, I can simply say that this is equal to probability of B into probability of A given that B has occurred, using conditional probability, isn't it? There's a lot of dogs barking, so I'll have to stop the recording and start off once the dogs have stopped barking. Okay, I'm back. You know, you see these street dogs, they start barking for no reason. They haven't stopped it. I thought they had. I'm making this video at 12 o'clock in the night, so I'm supposed to be expecting all these things to happen. Okay, alright, fine. So can I now write probability of A to be equal to probability of E1 into probability of A given that E1 has occurred plus probability of E2 into probability of A given that E2 has occurred plus it goes on like that, and then I have probability of En into probability of A given that En has occurred. Now that is my total probability. That's all it means, nothing else. Okay, which can actually be written in summation notation as this: probability of A is simply equal to summation of I is equal to 1 to n probability of EI into probability of A given that EI has occurred. That's my total probability. Okay, fine. Let's look at this. What does it state? The probability of this particular event A to happen is in this section, or let's take this big chunk. Okay, in this big chunk here, it is nothing but probability of E1 occurring, which is this, if I'm considering this as E1, okay, into probability of A given that E1 has occurred. So here, first of all, E1 has occurred. Because E1 has occurred, under that, how many times is A occurring? That is conditional probability. If you want to understand that in respect to the diagram, that's what it means. So that is my total probability. Now, making use of this, I'm going to try and explain to you what is Bayes' theorem. Okay, fine. Let's go back and see what is Bayes' theorem here. Okay, for us to understand Bayes' theorem, I'm going to give you an example here. Let's say I have a bag. Okay, this is a bag, and I'm going to have, let's say, 4 bags. 3 and 4. Okay, So if I want to find out the probability of a red ball being picked out of all these things, how do I proceed with that? Very easy. I'm going to consider this as E1, and this bag is picking up this bag as E2, and this as E3, and this as E4. Now, because all the four bags has equal chances of being picked, I know that probability of E1 is going to be equal to probability of E2, and that's going to be equal to probability of E3, and that is probability of E4, which is 1/4. Okay. All right. Now I'm going to define event A as choosing a red ball. Okay. Now once I have defined my event as choosing a red ball, I'm now going to find out what is the probability of choosing a red from the first bag, which is probability of A, given that the first bag has been chosen. Okay, how many reds are there in the first ball? 1. And how many overall? 1, 2, 3, 4, 5, 6, 7, 8, 9. So probability of A, given that E1 has occurred, is 1/9. Okay. Okay, perfect. Similarly, I can find the probability of A given that E2 has been picked up, or probability of getting a red ball from the second bag, which is 4 divided by 10. And I can also find out probability of A given that E3 has occurred. How many reds in the third bag? Let's check that. 6 out of 10. 6 out of 10. And at the last, I have probability of A given that E4 has occurred, which means I've chosen the last bag. What is the probability there? Let's check that. I have 8 by 10. Okay, 8 by 10. So probability of picking a red ball is simply equal to probability of first ball being picked into probability of A given that the first ball has been picked. First bag has been picked. Then probability of E2 into probability of A again given that the second bag has been picked, plus probability of E3 into probability of A. I'm just going to scroll to the right, given that E3 has been picked, and then I have probability of E4 into probability of A given that E4 has been picked. Okay, perfect. Now what is the probability of E1? I've already found that as 1/4 into probability of A given that E1 has occurred is 1/9 plus 1/4 into A given that E2 has occurred is 4/10 plus again 1/4 into, sorry, going to be into here, into probability of, okay, this is for this, this is for this, and I'm doing this, probability of A 6 by 10 plus then probability of, that's 4, E4, and 8 by 10. So that's my probability. I'm just going to sum that up very quickly. It's going to be a 1/36 plus 4/40 plus 6/40 plus 8/40. Okay, now I'm going to make a slight change here. I'm going to add another blue ball to my first bag because I want to make the denominator to be the same. So 1, 2, 3, 4, 5, 6, 7, 8. I'm going to add a 9 to this. So total possible options here is a 10. So when that change has been done, there's not going to be any more changes with respect to the probability. That's going to remain the same. It's only that this particular denominator will now become a 40 and this is going to become a 10. So my probability here will be a 10 because now I have 10 options to choose from. Okay, so with that being said, what is my probability? It's going to be 6 plus 4 is 10, 10 plus 9, which is a 19 divided by 40. That's the probability of a red bag being chosen from any one of these three bags. Okay, So that is my total probability. Okay, what if a question something like this has been asked? Say you know that the red ball will be picked. Okay, you already know that the red ball will be picked. Okay, you already know that the red ball will be picked, but you want to find out from which one of these bags did the red ball was picked from. Was the red ball picked from? Now if you want to find that out, we need to apply Bayes theorem. Okay, so you get that, right? Okay, perfect. Now let's go back and look at Bayes theorem. I'm going to bring up the statement on Bayes theorem for you. So that is the statement on Bayes theorem. It's a very easy proof. Actually, if you can see this, it's again going back to talking about E1, E2, E3, and so on and so forth being mutually exclusive and exhaustive events. That's what it means by pairwise disjoint and partition of a sample space. Okay, so well, it's a very easy proof. Let me tell that to you. Let me tell you that what it is. Well, we already know that probability of EI beat any event given that A has occurred can be written as probability of A intersection EI divided by probability of A, isn't it? That's the conditional probability, isn't it? Now this further can be written as probability of EI into probability of A given that EI has occurred divided by, this is the total probability, which is summation of probability of EI into probability of A given that EI has occurred. Okay, so that is my Bayes theorem. That's all, nothing much. Okay, we will be looking at more questions on Bayes theorem and understanding how to apply Bayes theorem. The statement is very easy. The total probability statement is also very easy. When we are applying this on the questions, that's when it becomes a bit tricky, because you need to identify your events, which is EI and which is your event A, and so on and so forth. Okay, we'll be looking at a lot more examples on that. I'm going to stop the video over here. Thank you for watching the video. As always, go ahead and subscribe for the video. Ask your friends to watch this video, share the video, and like the video. Any questions, any suggestions, please post that on the comment section. Thank you.